Hi, and welcome to the fifth lesson on dynamics. We're going to talk about angles, slopes, and ramps. When we did this, we looked at it in kinematics as well, where we looked at where objects were launched at angles from a bunch of different things that were not horizontal or were not parallel or perpendicular or at nice things. And what we did, just as a little reminder, is we had to break things up into components. We had our x components and our y components. So we talked about what the total initial velocity was, and we would also talk about what the x component of the initial velocity was and the y component. So what I can do is I can take this and I'm going to make it bigger so that we can look at it a little bit. That would be our vector triangle or our vector sum. And we can do a little refresher of what those component angles are. If I was to find the sine of this theta, that would be equal to opposite, which is Vy, over a hypotenuse, which is my V total. So my component, Vy, would be equal to V total times sine theta. If I looked at my cosine ratio, cos of theta is equal to adjacent over hypotenuse. The adjacent is Vx in this particular case, and my hypotenuse is still V total. So Vx can be found with V total times cos theta. And we're going to have to apply a very similar method when we do examples in dynamics as well. So if you need a little bit of a refresher on those trig ratios, maybe take a look back at the stuff that we did on kinematics. Let's look at an example that is a dynamics example. We can write example 1 here if we want. A child in a wagon is 40 kilograms and is pulled along a horizontal road with a 400 Newton force at a 35-degree angle above the horizontal. What is the acceleration of the wagon? So if we want to, again, I like to draw little pictures. There's our wagon. Our handle goes up at an angle, just sort of like it normally would. And then that angle, which they give to us, is 35 degrees. And again, this isn't a free body diagram. I've actually drawn the wagon. I've actually drawn the ground. I don't necessarily need that. So if I was going to draw a free body diagram, I really like the idea of drawing our free body diagram as dots. I think they work really well for all these examples that we're going to do today. So I've got this child in a wagon, which is 40 kilograms, and it's pulled with a 400 Newton force. So that's going to be along the line of the handle. And I'm going to call this my applied force. And if I want to, I can add here that this angle is going to be 35 degrees. I think that'll be pretty useful. I'm starting to decide that maybe this diagram is a little small, so I'm gonna make it a bit bigger. Yeah, that looks way better. 35 degrees. As well, since my wagon is on the ground, it's close to Earth, so there's going to be a force due to gravity on it. And since it's against the ground, there will also be a normal force pointing upwards like that. So this is my free body diagram. Notice that my normal force and my gravity force due to gravity, are entirely in my y-plane, but my applied force is both in my x-plane and my y-plane. So what I'm probably going to have to do, wow, I can tell you, I'm definitely going to have to split it up into components. I will have one component, FA, in my x-plane, and one component, FA, in my y-plane. That's typically how this is drawn. If it asks you for a free body diagram, usually we don't draw the components in. So if this is a marked free body diagram, if myself or another teacher in your future physics career asks you, please draw a free body diagram, I don't include those purple vectors unless they explicitly ask for them. Just do those red ones, which are the forces that are acting on that wagon. So the question is, what is the acceleration of the wagon? So we connect the acceleration of the wagon to our dynamics unit with Newton's second law, F is equal to ma. We have an option again. We can look at our x-plane and our y-plane. I think since the acceleration is in the x-plane, it would be intuitive to look at that first. However, before we get there, just because I know what's happening, I would like to look at my y-plane first. So I'm going to do that one first. Fy is equal to ma. Previous to looking at things at angles, we have only had the normal force and the force due to gravity in our y-plane. But we'll see that now we have an applied component in our y-plane. So we have three forces. I'm going to call to the up and right positive so that my F net statement is I've got a positive Fn, I've got a positive Fay, and I have a negative force due to gravity. My normal force is pointing up, my applied force in the y-plane is pointed up, and my force due to gravity is pointed down. And that's going to be equal to ma. We have to remember that this is the a in our y-plane. Is it accelerating up or down? And it's not. We've got a wagon that's being dragged along a road. There is no up or down motion. So since my acceleration in my y-plane is 0, my net force is then equal to 0. What I would like you to notice now is that Fn is not going to be equal to Fg. If you've memorized that, despite my many warnings not to memorize that, this is definitely where you're going to run into trouble. If I rearrange this equation, I end up with an Fn is equal to Fg minus Fay. Notice how now the normal force is going to be less than the force due to gravity by the little bit that you're pulling it up. The force due to the normal force no longer has to entirely support this wagon because you're physically pulling it up in the air a little bit. I can substitute something in for Fg just because I know that I'm going to need it in the future. If you didn't think about that right now, then that's okay. Fay, and my Fay I also might as well do while I'm here. Fay, this is the opposite of my angle. So opposite is a sine. Maybe I can do that right here. Sine theta is equal to opposite, which is Fay, over my hypotenuse, which is Fa. If I rearrange, I find that Fay is equal to Fa sine theta. Fa sine theta. And that would be the expression for my normal force. Fx is ma. So now I'm going to go back and look at, I'm stumped there. I could actually probably find the magnitude of my normal force, but I don't have an acceleration there. So I'm going to go back to my x-plane. Fn isn't really helping me get to an answer right now. I'm going to go back to my x-plane, and I'm going to look at my x-plane. In my x-plane, I only have one force, and it is in my positive direction. So I'm going to write Fax is equal to ma. I only have one force in my F net statement. Fax, if I look at x, it's a cos, it's adjacent. So cos theta is equal to adjacent over hypotenuse, which means that Fax is equal to Fa cos theta. And I can substitute that into my Newton's law expression, and I get my Fa cos theta is equal to ma. So that my acceleration is equal to Fa cos theta divided by m. My acceleration, I got to scroll up a little bit to look at what that was. So I think that was a 400 Newton force times cos 43. Is that a 43? No, that's a 35. Divided by my mass, which is 40. And as most of you probably saw, I've got that written down here. I can pull that up. So my acceleration in this instance is 8.19 meters per second squared. And it turns out that I didn't need to look at my normal force in this instance. I still think it was well worth pointing out that even in this instance, our normal force is not equal to Fg. There's this little bit extra over there. Let's take a look at example number 2. Mr. Collins attaches a rope to his broken down Volvo, which is 750 kilograms, and pulls it along a horizontal road with a 5,600 Newton force at 20 degrees above the horizontal. If the Volvo accelerates at 3 meters per second squared, what is the coefficient of friction between the Volvo and the ground? So, if you want to, you can draw a little picture of the Volvo again. Instead, I'm just going to go straight to my free body diagram. I know that on Earth, I'm going to have a force due to gravity going down. I am going to have a normal force going up if I'm getting dragged along the road. It also tells me that I am applying a force, Fa, at a, and notice how I try and only draw the forces in red. Nothing else gets drawn in red so that I know that only forces are in red. A 20-degree angle. It also tells me that there's going to be a force of friction by asking what is the coefficient of friction. It's going to work against that applied force, against that force of motion. And that would be my free body diagram. Again, our applied force will have components in both the x-plane and the y-plane. And we're going to have to figure out what those are. Fay, Fax. Sometimes my y's look a little bit like x's, so I'll try and do that one again so it looks a bit better. Fay. And what I might do, those pink ones or purple ones, is I'll sort those out first because I know I'm going to use them. So I've got a sine theta is equal to opposite over hypotenuse. So that Fay is equal to Fa sine theta. And cos theta is equal to Fax over Fa. So Fax is equal to Fa cos theta. Some people get in the habit of memorizing these, which I don't like because they don't always give you the exact same place for the angle, and sometimes you have to think about it for a bit, but most of the time they're pretty similar. So let's start by, while we're well beyond starting, let's take a look next at our Newton's laws. So what I've done here is I think I've just taken a little bit of a list of the important information from this question and written it down there so I can substitute it in later. So Newton's second law, we can apply it to either the x-plane or the y-plane again. Coefficient of friction makes me think, hey, I'm going to look at the x-plane first. I have two forces in my x-plane. I'm going to call to the right and positive, which means I have a positive Fax and a negative Ff, and that is equal to Max. You'll notice that I usually start my Fnet statement with a positive force. The only reason I do that is because if you lead it with a negative Ff plus Fax, that's completely fine. But sometimes your negative sign doesn't look good and you lose it. You just think it's an accidental mark on a page and then it turns into a positive force and then you end up with the wrong answer. So this is mathematically accurate. It's a fine process to engage in. It's just maybe because I make mistakes, and this is one way that I avoid making mistakes, is by starting with a positive force. From my formula sheet, the force of friction is equal to mu Fn plus Fax, which I did up here in purple, is Fa cos theta, and that's going to be equal to Ma. So when I take a look at this expression, what I'm looking for is do I know all of my variables except for one? I'm looking for mu, so it's an okay thing that I don't know that, but I don't know what Fn is. I know what Fa is, I know what theta is, I know what my mass is, and I know what my acceleration is. So the only thing I'm missing before I continue is Fn. And this is where, if you if you write down Fn is equal to mg, if you've memorized that, even though I've told you not to, this is where you're going to end up making a mistake. I don't know what Fn is off the top of my head. I'm going to have to look at the sum of my forces in my y-plane, and that's going to be equal to MAY. AY is going to be 0. I'm not accelerating up or down off my road. And my Fnet statement, I have 1, 2, 3 forces there. FAY is going to be positive, FN is going to be positive, and FG is going to be negative, and that's going to be equal to 0. I'm looking for Fn, so if I rearrange, I get Fn is equal to Fg minus Fay, which makes sense because my normal force should be a little bit less than gravity, or depending on how hard I pull up, it could be substantially less than the force due to gravity. I can then take this equation, which I can put a little 1 beside, and substitute it into this equation, which I can put a little 2 beside. So I end up with a mu times Fg minus Fay plus F. Oh, and see, I dropped that negative sign out in front. There, I went back and put it in. Plus Fa cos theta is equal to Ma. Fay, I've derived up top again because I knew it was coming, is an Fa sine theta, negative mu Fg minus Fa sine theta plus Fa cos theta is equal to Ma. And if I rearrange this so that I solve for mu, I think what I get is a mu is equal to Ma minus Fa cos theta divided by a negative Fg minus Fa sine theta. And now I conveniently have this list of known variables written down on my left. My mass is 750 kilograms. My acceleration is 3. My applied force is 5,600. Goes 20. That doesn't need a bracket. Divided by a negative Fg is 750 times 9.8 minus 5,600 sine 20. I think if I scroll down here, I have in fact figured out mu already, and I end up with a mu is equal to 0.554. Mu is a unitless variable, so I'm done. We can move on. Example 3. A Physics 11 student, 67 kilograms, slides down a frictionless slide that is 36 degrees to the horizontal. What is the student's acceleration? I went ahead and I drew a little angle at about 36 degrees. It's definitely not to scale. I just liked my straight lines. This is where, for drawing a free body diagram, our dot is going to help us a lot. So we're just going to draw a dot. That's our Physics 11 student. You can ignore that little purple thing down below for right now, but it will come up later. So on the dot, this is a little bit more complicated. We have the force due to gravity will always act downwards towards the center of the earth. G. And actually, I'm gonna move where I wrote Fg. I'm just gonna draw it over there, and you'll see why in a second. Your normal force does not always act upwards. If you're flat on the ground, it does, but that's only because it acts perpendicular, which means at 90 degrees, to the surface that you're on. So it acts this way. That's our normal force, perpendicular to the surface. So the weird thing about the ramps, and this is our trick, and if we were in a classroom, what I get you to do, and you can look at it right now. If you're looking at your computer screen, it's less useful if you're on your phone. And then you just tilt your head 36 degrees to the left so that your eyes line up with that ramp. And that is going to be the plane that we're going to use. We're going to cheat a little bit. We're going to use this trick. And we're going to call this our y plane, up and down, so that the normal force is in the y plane. And we're going to call left and right along the ramp our x plane. So it's not straight up and down. We've tilted our axes a little bit. And what we've done is we've made sure that our acceleration, our movement, is all in one plane. It definitely simplifies the approach so far, so much so that I won't even go into the math to do it the other way. It's possible, but it's definitely unkind. You definitely want to take your axes, you're going to tilt them 36 degrees so that all of your motion is in the x plane. You will notice then that your normal force is all in your y plane. It's straight up and down. It's parallel with that y-axis. but our force due to gravity is not. We are going to have to break it up into components. You can break it up into components two ways that make sense here. You want them to be perpendicular to and parallel to. Actually, I don't. Yeah, sorry. I wanted the other way is a little bit easier. I can show you that way too. Yeah, I want to go this way. I think it's easier if you draw your parallel vector first and then your perpendicular vector after. So these two vectors need to be at right angles to each other. I'm going to move my axes out of the way just a little bit there, and then actually I'm going to redraw this, and just because it's getting a bit small, I'm going to have to write some numbers in there. You'll notice how big I have made this, and it's because there's some things that we got to fit in here. Don't be afraid to draw very large diagrams. This will be our FG in the X plane. This will be our FG in the Y plane. Okay, so we now have our triangle where FGX and FGY are at right angles to each other, but we don't know any other angle in that triangle. We need to find one. You will notice that if I extend my FG straight down, since it's going straight down and this is a horizontal, this is a right angle triangle going straight down with a 36 degrees to my left. It's usually best practice to use the angle that they give you. So they're giving me 36 degrees. So that's the angle that I'm going to try and use throughout this question. But you might see along the way that there's another angle you can use. So if this is 36 degrees, then the missing angle in my triangle is going to be 36 plus 54 is 90. Therefore, this angle is going to be 54 degrees. And now if I look at this triangle, which is also a right angle triangle, my missing angle down there has got to be 36 degrees. So what I'm going to do is I'm going to get rid of this angle. Oh no, let's try that again. I'm going to get rid of this angle, and we're going to use the angle that they've given us here is 36 degrees. By now, you should recognize that what you're going to have to do is you're going to have to find the magnitude of those components. So I'm going to do that first. The sine of theta, which is 36 degrees, is opposite FGX x over hypotenuse, which is going to be FG. If your force due to gravity is not the hypotenuse, you have made a mistake. Anytime you are breaking things up into components, the original thing should be the hypotenuse. That means that FGX is going to be equal to FG sine theta. If I look at cos theta, that's going to be FGY. FGY is adjacent to cos theta, and FG is still my hypotenuse, so that FGY is equal to FG cos theta. I'm going to go back again, and we are going to have to look at Newton's second law again. We're going to start with sigma F is equal to ma. I'm definitely going to look in the x-plane this time because that's the plane that I'm accelerating in. I only have one force in the x-plane. It is a component of the force due to gravity. In a right angle triangle, a component must be less than the hypotenuse. So you're going to be going down a ramp slower than you would if you were in free fall. And this should intuitively make sense. FGX is going to be equal to MA, and FGX is an FG sine theta equals MA. FG, straight off your formula sheet, is always, if you're on close to the surface of the Earth, mg. Sine theta is equal to ma. And you should notice something right now about the left-hand side of your equation and the right-hand side of your equation. You should notice that they both have an m in it. So I can divide both sides by m. And I realize that this equation is independent of mass. G sine theta is equal to a. This is incredibly useful for things like roller coasters and water slides because it means that different massed things or different massed people or different mass roller coaster cars will accelerate the same way and act in a predictable manner. So that if you had a really heavy roller coaster, you don't end up flying off the rails, or if you have a really light roller coaster, you don't end up flying off the rails. Things act in about the same way. If you know the sine function well, the sine of 90 is 1. So if this was tilted up, if the 36 degrees was tilted up to 90 degrees, you would essentially have an object in free fall. That slide, that ramp would be straight up and down, and our acceleration would then be equal to g. And as you get closer and closer and closer to 0 degrees, the sine of 0 is 0. So if you were on a flat horizontal ground, you wouldn't accelerate at all. So this little neat equation, I like how much it simplifies, it should be fairly intuitively accurate. So acceleration is going to be 9.8 sine 36. And I think I've written down that answer. And our acceleration to 3 sig figs is going to be 5.76 meters per second squared. I think I have one last example. This movie might turn out a little bit long, it looks like. A puppy and its human friend are playing on a slide that is at 24 degrees to the horizontal. The human gives the puppy an initial velocity of 3 meters per second up the slide, and the coefficient of friction between the puppy and the slide is 0.12. How far up along the slide does the puppy get before they start coming down? There's a lot of things happening in this question. And it takes a bunch of little pieces that we've talked about already and puts them together. One of which, if you didn't pick up on it the first time I read it, it gives you an initial velocity. And if you hear initial velocity, you should kind of be getting twigged in the back of your brain. You should be like, oh, that initial velocity is from kinematics. I might have to use some of the kinematics things to solve this. So let's take a look. We're going to start the exact same way. We're going to start with a free body diagram. I like the little dot method. And I'm going to do my forces. I've got a force due to gravity going straight down. And I've got a normal force that's going to be perpendicular to the surface. And then I also have a force of friction. It gives us a coefficient of friction. So there is going to be a force of friction. So if the puppy is traveling up, and I'm going to draw this away because I don't have any arrows on my free body diagram that aren't forces. We're going up, then my force due to friction is going to be downward. This will be my force due to friction. I am again going to have to split my force of gravity up into components that are going to be parallel to the surface and perpendicular to the surface. So this is our right angle between our components. This will be our FGY. This will be our FGX. I can, if I want, continue to, this will be the angle theta, as we proved in the previous question. So let's go through our sine and cos again. Our sine of theta is going to be equal to our opposite, FGX over FG, so that FGX is equal to FG sine theta. If I look at cos theta, that's going to be equal to FGY over FG, so that FGY is equal to FG cos theta. And then I've just kind of got that little derivation out of the way. A bunch of people at this point will start jumping straight to these. It's good to figure out your picture first. But if you've started memorizing that FGX is FG sine theta and FGY is FG cos theta, as long as you are solid about where that angle is coming from, I'm completely fine if you jump there. So how far up along the slide does the puppy get before they start coming back down? So if I take some of these details from the question, I have my acceleration is 3 meters per second squared. Did I make myself a list? I did make myself a little bit of a list. I have my initial velocity is 3 meters per second squared. I have my coefficient of friction is 0.12. And I also can tell one more thing from the question. You should be challenging yourself and ask, do I know one more thing? I do know my final velocity, because I want to know how far up along the slide it gets before they start coming down. So as you switch directions, your velocity must, for a brief instant, be 0. And those are all the important details from the question. I have an acceleration there, and that is incorrect. I don't know why I wrote that. My velocity is 3 meters per second. What I'm going to need to find as an intermediate is my acceleration. So we're going to have to apply Newton's second laws, and I would intuitively look in my x-plane because I'm accelerating along the ramp. Is equal to ma. Now I have to decide which direction I want to be positive and which direction I want to be negative. It's up to you. I frequently advocate that you should choose your initial direction of motion to be positive, but I sometimes advocate that the direction of acceleration should be positive. And in this case, they're both opposite directions. So let's just be consistent. Let's call my initial direction of motion positive, which means that both of my forces, negative FF and Fg are both negative, and that'll be an Fgx component, and that's equal to ma. Ff, my force of friction from the formula sheet, is negative mu Fn. Fgx, which I've derived up above, is going to be an Fg sine theta is equal to ma. I'll notice as well that they didn't give me a mass for my puppy, so I'm really hoping that what happened in the previous question will happen again, and I'll figure out that it's independent of mass. So right now, I don't know what my normal force is, I don't know what my mass is, and I know that Fg relies on mass, so I'm a little bit stumped. I'll double check my work. I'll be like, did I make a mistake? Am I stumped because I made a mistake? Or am I stumped because this is like really a dead end? And I'll be like, oh, I don't think I've made a mistake yet. So I'm stumped, which means I have to look in my y-plane. It's really the only thing left. I'm not accelerating off the ramp or into the ramp, so my acceleration is 0. And in my y-plane, I have a normal force, which I'm going to call positive, and I've got an Fgy, and that's going to be equal to 0. So that my normal force is going to be equal to Fgy, and my normal force is going to be equal to Fg cos theta, which was derived above again. I'm going to skip a line just so I have a little bit more space. I have a negative mu. I've got my normal force, which is Fg cos theta minus Fg sine theta is equal to ma. Notice how I'm not skipping any steps. I don't want to do too much in my head. I'm just changing kind of one thing at a time and rewriting the line down, and I'm just kind of letting the algebra come out itself. Negative mu mg cos theta. And this is the exact steps I went through when I solved it myself. I'm not doing extra steps just to make it harder. I'm writing down the exact process that I personally used to solve this when I came up with the answer that I'm pretty sure I wrote down below. And again, we'll notice that every single term has mass in it. Every single term. So my right hand mass cancels, and on my left hand side it does as well. And I come up with that my acceleration is equal to negative mu g cos theta minus g sine theta. And I unfortunately just wrote down my displacement. I don't have an intermediate answer for you right now. I would definitely plug this into my calculator and get an answer. I believe it's about 10. But I'm going to keep going. I'm not going to pause to type that in my calculator right now. I will let you guys do that. Once I have my acceleration, I can use a Vf squared is equal to V naught squared plus 2AD. My final velocity is 0, which means I get negative V naught squared over 2D, over 2A is going to be equal to my displacement. And if I plug that in appropriately, I should get that I'm only going up a little bit. Just like someone playing with their puppy dog on a slide, sliding them up a little less than half a meter and letting them come back down. Everybody's having a great day in the park. Thank you for watching, and I just wanted to remind you guys a couple of keys for success. Number one, you got to do the practice questions. If the things I'm saying make sense, that's phenomenal, but you still have to practice and make some mistakes on your own. And that goes along with number two. If you get stuck, ask me questions, get in touch, write me an email, make an appointment. or leave a comment on the YouTube video. And step number 3 to success is look after yourself. Eat good food, get some exercise every day, and socialize as much as you can right now. I hope you guys are all doing well, and I will talk to you soon.